Okay, hello and welcome everybody. This is the worked examples section for matrices and matrix multiplication. And we're just going to jump right into things, aside from me reminding everybody that this is the Kronecker delta function, defined by 1 when I equals j, and 0 when I is not equal to j, and the identity matrix, which has a 1 along the diagonal. And this could continue if I wanted it to. Is written as, in shorthand, as the Kronecker delta function. I and j go from 1 to however big the dimension is. And corresponds to the linear map L x1 x2 dot 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 xd for d dimensions is the input and the output are the exact same. So that's why we call it the identity, because it behaves like the identity on the input and the output. Let's look at a nice example here, or an exercise, and we'll consider the linear map L of x, y, z, and let's say the output is 2x plus y, 2y plus z, 2z plus x. Let's compute L of L of L of 1, 0, negative 1. Well, we've got a few choices. We could go piece by piece if we want to. Definitely nothing preventing us from going piece by piece. You can start there, you then go there, you then go there. Or we could represent L as a matrix and compute 3 powers of the matrix. Because really, this is just L cubed of 1, 0, negative 1. Considered cube as matrix multiplication or function composition, however you want to think about it. Let's go ahead and represent L as a matrix. So what I need to do is I have to look at the coefficients here. And it looks like my coefficients should be 2, 1, 2, 1, 2, 1. Or should they? So I want everybody to pause right here and figure out what I did wrong. One thing I should note is that the input is 3 dimensions. And actually the output is also 3 dimensions. And a matrix with 3 inputs and 3 outputs should be 3 by 3. So that means I'm missing an output. Technically that's an input. It means I'm missing an input. What should go there? And I think when people realize what should go here, these should be the coefficients on z, you start to realize that in fact these were, in some cases, the wrong numbers in the first place. So let's rewrite everything in terms of x, y, z, x, y, z, x, y, z, and look at the coefficients up here. Coefficient is 2x plus 1y plus 0z. It's 2y plus 1z plus 0x, and it's 1x, 0y, and 2z. And at this point, now I have my matrix represented correctly. I pulled a little bit of a sneaky on you up top. So this is now my actual matrix. And I can go ahead and compute matrix powers. So let's go ahead and compute 3 copies, because I'm going L cubed, 3 copies of this matrix. So 2, 1, 0, 0, 2, 1, 1, 0, 2. And then my third matrix, 2, 1, 0, 0, 2, 1, 1, 0, 2. And at this stage, I think a lot of students asked a very important question. Does the order I multiply in matter? And that's a perfectly valid question. It's really important that you are asking the question, even though in this case the answer is no, because there are certainly cases where the answer may be yes, but in this case the answer is no, and so you can make a choice. This is called the associative property, by the way, if you ever care about names. I can make a choice to calculate that matrix multiplication first if I want to, or I could calculate this one if I wanted to. And in fact, this is true even if I don't repeat the matrices. I think it makes a lot more sense when I'm repeating the same matrix 3 times in a row. You would think, of course, it should be true that the order doesn't matter. But in fact, the order doesn't matter even if I'm putting distinct matrices in each place. So with matrix multiplication, the difference between left, right, and middle matters. You can't exchange terms across each other. But aside from left, right, and middle, the actual order in which you perform the multiplication itself is not going to matter. So let's go ahead and follow the green direction and perform that multiplication first. Recall what I'm doing. I'm separating the left matrix into rows and the right matrix into columns. And then I'm computing all possible linear combinations of rows with columns. So if I just start and start going for it, and then I put the number in the overlap, I'm going to go ahead and start, and I just look at the top and the left, and what I get is 2 squared plus 1 times 0 plus 0 times 1. If I do the top in the middle, I have 2 times 1 plus 1 times 2 plus 0 squared. If I do the top and the right, I have 2 times 0 plus 1 squared plus 0 times 2. If I do the middle left, I have 0 times 2 plus 2 times 0 plus 1 squared. If I do the middle in the middle, I have 0 times 1 plus 2 squared plus 1 times 0. If I do the middle in the right, then I end up with 0 squared plus 2 times 1 plus 1 times 2. If I do the bottom left, I have 1 times 2 plus 0 squared plus 2 times 1. If I do the bottom times the middle, I have 1 squared plus 0 times 2 plus 2 times 0. If I do the bottom and the right, I have 1 times 0 plus 0 times 1 plus 2 squared. If I go ahead and simplify all of the terms that I've written out, it looks like I've got 4 plus 0, I've got 4 plus 0, and I have 1 plus 0. I've got 1 plus 0, and 4 plus 0, and 4 plus 0, and I've got 4 plus 0, 1 plus 0, and 4 plus 0. Lots of 4s and 1s sitting around. But anyway, that's going to be me calculating those two magenta terms together. And then what I'm left with, basically, is this final term that I need to pull down, which will still be a 2, 1, 0, 0, 2, 1, 1, 0, 2, and multiply against this other matrix I've already computed. And we're going to compute that multiplication the same as before. So now the matrix on my left becomes rows, the matrix on my right becomes columns, and I go ahead and compute just as I did before. So what I end up with here is, if I take the top against the left, I have 2 times 4 plus 1 times 1 plus 0 times 4. Top against the middle, I have 2 times 4 plus 1 times 4 plus 0 times 1. And then the top against the right, I have 2 times 1 plus 1 times 4 plus 0 times 4. The middle against the left gives me 0 times 4 plus 2 times 1 plus 1 times 4. The middle against the middle gives me 0 times 4 plus 2 times 4 plus 1 times 1. And the middle against the right gives me 0 times 1 plus 2 times 4 plus 1 times 4. The bottom times the left gives me 1 times 4 plus 0 times 1 plus 2 times 4. The bottom against the 0, the middle gives me 1 times 4 plus 0 times 4 plus 2 times 1. The bottom times the right gives me 1 times 1 plus 0 times 4 plus 2 times 4. If I go ahead and compute all 9 of these terms, I'm left with the 3 by 3 matrix. It looks like I have 8 plus 1, so 9. I've got 8 plus 4, so 12. I've got 4 plus 2, so 6. I've got 2 plus 4, so 6. I've got 2 plus 4, so 6. I've got 2 plus 4, so 6. Sorry, 8 plus 4, so 12. I then have 8 plus 4, so 12. I have 2 plus 4, so 6. And I have 8 plus 1, so 9. And I'm seeing now that my middle should also be 9. It's nice to have something that's a little bit symmetric from the beginning. You start to realize if you may have made a mistake. But yes, definitely. Now this is the correct matrix. And we can finally try to answer our question. What was the question? I wanted L of 1, 0, negative 1. And so what we've established here is that this the triple composition of linear maps, L cubed on x1, x2, x3, ends up giving me exactly what I've calculated along with the x1, x2, and x3. So I have 9x1 plus 12x2 plus 6x3. I have 6x1 plus 9x2 plus 12x3. And I have 12x1 plus 6x2 plus 9x3. Which means if I evaluate at 1, 0, negative 1, that's a 1, a 0, and a negative 1, and I'm just putting in a 1, a 0, and a negative 1, 1, 0, negative 1, 1, 0, negative 1, to give me the vector 9 plus 0 minus 6 is going to give me 3. I can do 6 plus 0 minus 12 is negative 6, and 12 plus 0 minus 9 is 3. It's a very nice way of calculating the triple composition of a linear map just through matrix multiplication. Okay, and we haven't really run into any of the cases when writing matrix multiplication and Einstein's summation would be useful. We actually won't probably in this course. It is something that physicists get into quite a bit, and actually me and my own research have gotten into it as well. But the calculations are actually quite complicated, even though at the end of the day they do condense the notation a lot. I will prepare us all for those situations with the following exercise, though. So the following exercise is that we're going to find a double index notation for the matrix 1, 2, 3, 0, 1, 2, 0, 0, 1 using delta I, j, and shifts of delta I, j. So this is where Einstein's summation would end up being useful if we could write this in some sort of condensed notation, m, I, j, as some function of I and j. Now I want to note, because I didn't do a very good job of this in the last video, every time we see these i's here, we should think about these as the row number. And every time we see the j here, we should think about this as the column number. So column number would be like 1, 2, and 3, and the row number would be like 1, 2, and 3. And so that's what you should think with I and j. And we want to construct basically just a function of I and j so that when we put these numbers in, we actually get, when we put the row and the column number in, then they actually immediately give us the entry. So something like 2 for the, or 1 for the row and 2 for the column should give me a 2. 3 for the column and 1 for the row should give me 3, and so on. So let's see if we can do something like this with the matrix that we see here. Think of some function. So basically we just need a function f such that f of 1, 1 is 1. F of, let's see, row 2, column 1 would be 0. F of row 3, column 1 would be 0. F of row 1, column 2 would be 2. F of row 1, column 3 would be 3. F of row 2, column 2 would be 1. F of row 3, F of row 2, column 3 would be 2. F of row 3, column 2 would be 0. And F of row 3, column 3 would be 1. There's a reason why I said using delta and maybe shifts of delta is because if I look down the diagonal, I see a lot of 1s. And this characteristic of two numbers as my input and then my output being a 1 is exactly delta ij. But that only gives me the diagonals, right? Delta ij you can kind of think about as 1, 0, 0, 0, 1, 0, 0, 0, 1. So I'm going to have to play some other games kind of over here, right, on those three terms. The zeros are kind of already included. I kind of already have all of that, but I need to figure out what needs to go in the top right. So let's figure that out. What sort of function, or maybe a version of delta, can give me 2's here? What about something like twice delta? Well, unfortunately, twice delta would give me 2's here, but this is why I said maybe a shift of delta. How can I shift delta? I want to shift delta to the right. That means I'm going to move either a row up or a column to the right. Well, if I is a row and I want to move it up, I can make it I plus 1. And then all of a sudden, the 2's shift from being on the diagonal to being exactly one above the diagonal. And I can play the same game with my 3 here by playing delta 1 or I plus 2. I can shift up 2 rows in j and multiply it by 3. And then I get 0, 0, 3, 0, 0, 0, 0, 0, 0. And at this stage, if I add all of my deltas together, I can recover my actual f. So in other words, I could say that the matrix Mij, rows and columns going from 1 to 3, can be written as delta Ij plus 2 delta I plus 1j plus 3 delta I plus 2j. I goes from 1, I and j goes from 1 to 3. So that sets you up for some Einstein summation if you want to use it. Like I said, I actually use this a lot, but I really can't expect too many of you to run into it that often. It's good to keep in mind, though. It really lends itself well to algebraic manipulation, because at this stage, I can just algebraically take powers of that this collection of objects. I can think about them as just a collection of variables and then take their powers and FOIL everything out. And it makes it really efficient for computers. With that said, let's maybe verify that this representation of our matrix given here agrees with the original under powers. So let's consider the matrix 1, 2, 3, 0, 1, 2, 0, 0, 1 squared, as well as what I've just computed squared, and using the Einstein notation correctly. So let's go delta ij plus 2 delta I plus 1 j plus 3 delta I plus 2 j. And then if I were to multiply it by another matrix, keep in mind when I defined matrix multiplication using Einstein summation, it would be like the following. And so the second, notice that the second matrix gains the superscript, which is the subscript of the first matrix. So when I'm squaring this, I'm going to replace the superscript with the subscript of the first matrix, which was j in this case, and then give myself a new subscript. So 2j delta j plus 1k plus 3 delta j plus 2k. So we're going to compare those two. So let's actually compute the first case. Maybe I'll make it easier by moving this over and drawing out what it should actually be multiplied against. 1, 2, 3, 0, 1, 2, 0, 0, 1. And then I'm going to do all rows against all columns. When I do all rows against all columns, I end up with first row, first column, I have 1 squared plus 0 plus 0. Second row against first column, I have 0 plus 0 plus 0. The third row against the first column, I have 0 plus 0 plus 0. The first row against the second column, I have 2 plus 2 plus 0. Second row against second column, I have 0 plus 1 plus 0. Third row against second column, I have 0 plus 0 plus 0. And then the first row against the third column, I have 3 plus 4 plus 3. First row, or second row against the third column, I have 0 plus 2 plus 2. And then the third row against the third column, I have 0 plus 0 plus 1. Which, if I simplify everything, gives me the matrix 1, 4, 10, 0, 1, 4, 0, 0, 1. Now let's go ahead and use Einstein's summation. But to actually make it work here, I need to start by foiling. There's going to be 3 terms in each case, so I'm going to have to do all 9 cases of foiling here, which is going to be nice and enjoyable. So let's do the first against the first. That's going to be delta ij, delta jk, plus first times the second, 2 delta ij, delta j plus 1k. First times the third, 3 delta ij, delta j plus 2k. Let's do the second times the first. It's going to be 2 delta I plus 1 j delta jk. Second times the second is 4 delta I plus 1 j delta j plus 1 k. And then we can do the second times the third is going to be 6 delta I plus 1 j delta j plus 2 k. We're going to do the third times the second is going to be 6 delta, third times the first should be 3 delta I plus 2j delta jk. Third times the second is going to be 6 delta I plus 2j delta j plus 1k. And the third times the third is going to be 9 delta j I plus 2 j delta j plus 2k. Make sure I have 9 terms here. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, cool. So we foiled everything out. Now we need to figure out how we compute deltas. So there's a nice little proposition that I have that'll help us compute these deltas out. Proposition. Delta ij delta jk equals delta ik. That's definitely going to be true just because these are the identity matrix. So more or less the j's just cancel each other. And I also have another proposition. If I do delta I plus, let's do I plus n against j, that's the same as delta I against j minus n. And that's just true because we're computing whether or not this is true. So that's equivalent to me saying I is questionably equal to j minus n. So that's why we can get away with both of those properties, and that's going to help us compute these above. It says that I can cancel when the lower and upper index are the same, and I can also swap my shifted terms. So here I can cancel, and I end up with delta ik. And here I can shift that down to a minus 1, and then I can cancel, and I get 2 delta I k minus 1. And then here I can shift that down to minus 2, and then I can cancel, and I get 3 delta I k minus 2. And then here I can, I don't even have to shift anything down. I can just cancel, and I get delta I plus 1 k. And then here I need to shift that down to a minus 1, and then I can cancel to get 4 delta I plus 1 k. Then here I need to shift that down to a minus 2, and then cancel to get 6 delta I plus 1 k minus 2. Here I can just cancel to get 3 delta I plus 2 k. I can shift down and cancel to get 6 delta I plus 2 k minus 1. And then I can shift down to do minus 2 and cancel to get 9 delta I plus 2 k minus 2. And then if I wanted to go and do the reverse with all of these shifts in the k's, I certainly can, to make it plus 1, plus 2, plus 3, plus 3, and plus 4. What I'm left with, I can combine like terms then to give me delta ik. Count all the terms with an I plus 1 in them. I've got a 2i plus 1 and a 2i plus 1, so there are a total of 4 delta I plus 1 terms. And then calculate or compute the I plus 2 terms. I've got a 3, a 4, and a 3. So that's a total of 10 on the I plus 2s against k. And then my I plus 3 terms, I have a 6 and a 6. So I have 12 I plus 3k, and then one case of I plus 4 is the 9. And so what I see here is if I were to construct a matrix out of this, then the matrix that this gives me is my first delta, which is the diagonals, and some zeros. Then I have 4 when I'm shifted 1 row up, and I have 10 when I'm shifted 2 rows up. I would have a 12 and a 9 if I could shift any farther. So if I were in higher dimensions, then I'd have some 12s and 9s show up, but because I'm not in higher dimensions, I just have the 1, 4, 10, 0, 1, 4, and 0, 0, 1, which is exactly what the other computation gave me. Now, that was a whole lot of work, and I realize it's not going to seem like it makes any sense to do this Einstein summation. It really doesn't for us in this course, because we're going to try to work in low dimensions with fairly easy computations, but I just wanted to show you all an example of it kind of working. So I'll stop with that for the day. I hope it was interesting, even though you might not use some of this. I'll see you in the next video. Bye.